Hello everybody, my name is Emily Thomas and I'm here to present the dynamic systems theory. Before I begin, I feel it is important to note that this theory is a much more sophisticated approach to understand the complexities of the world around us than I make it out to be, and that is because my main goal is to break down the subject area of the theory and put it into simpler terms that not only makes it easier for us to understand, but to remember for our exams. Knowing this, it views systems as constantly changing, with different variables interacting with one another and creating feedback loops. This means that this theory is highly adaptive, which is why it has been utilized in various fields such as education, management, sociology, and psychology. So first things first, the dynamic systems theory, also known as dynamic pattern theory, coordination dynamics theory, ecological theory, chaos theory, and action theory, is a multidisciplinary perspective that seeks to understand how the complex systems of the world interact and evolve over time. This perspective attempts to explain how, why, and when various systems work together to form larger, more intricate structures. It studies how changes in one part of the system can cascade throughout the entire system, thus enabling researchers to make predictions about the system's future behavior. It is based on principles of physics, biology, chemistry, and mathematics, and is used in a wide variety of fields such as engineering, social sciences, medicine, psychology, and more. It studies both the physical and physiological behavior of an individual or group in order to understand how said individual or group changes over time. This approach is especially useful when applied to dynamic systems, which is just systems that undergo constant change over time. There's many varying ideas as to where the DST first came from, but it is commonly assumed that this theory originated from the mathematics and physics of Henry Poincare. This theory is the precursor to the chaos theory, the study of apparently random or unpredictable behavior in systems governed by deterministic laws, which you can see a literal diagram of on the right side of the slide. Poincare developed the chaos theory when he sought to understand the three-body problem. The three-body problem is a mathematical problem in which three objects interact with each other under their own gravity. Dynamic systems theory helps to clarify and explain the behavior of these objects, and it has been used to explore the behavior of complex systems in general. So, first piece of the dynamic systems theory, human motor control. This is a complex phenomenon that can be seen from the perspective of nonlinear dynamics. This refers to a system that changes abruptly in response to a small change in its environment. This nonlinearity manifests when a system responds drastically to a very small change in its surroundings or environment. A great example of this dynamic is when we gradually, over time, increase the temperature of a pot of water on the stove until it reaches 212 degrees Fahrenheit, at which point it rapidly boils. In this case, the water goes from a state of not boiling, we gradually increase the temperature to a state of boiling when it crosses that certain temperature threshold of 212 degrees Fahrenheit. A great example regarding humans and our response to different stimuli could be when the muscles in our legs suddenly presented with a difficult task. The muscles might initially fail to meet the challenge, but if our legs are presented slowly with the same difficult task, they will learn to meet the standards and perform as we need them to. This model allows us to understand motor control more completely, as abrupt changes in the environment can have an equally abrupt response in the system. Pattern coherence and stability in dynamic systems is often maintained despite changes in internal conditions or small external disturbances. For instance, this is the case in walking in high heels and chewing gum simultaneously. Although we're focusing on walking in heels, we can still chew gum, and vice versa. Although we're chewing gum, we can still walk in heels. However, when parameters or external conditions change, such as with surface slope, the old pattern may lose its coherence and stability. We may struggle to chew gum and walk in heels the same as we did before on a flat slope if the slope slightly inclines, if that makes sense. So in order to maintain coherence, the system must be able to adjust or adapt to its new environment, to the new stable state, which we'll talk about here in just a second. Theories of human coordinated movement have shown that a systematic change in one variable can produce a nonlinear behavioral shift. So if we look at our example of boiling water again, of course that's not a human coordinated movement, as the temperature is not something that we can make happening without any additional heat or a stove. But if we take this example, we know that the variable that's changing is the temperature of the water. So that changing temperature of the water is the systematic change in a variable, and then that causes a nonlinear behavioral change in the water. It's not linear in the sense that we're not just gradually boiling a little more and a little more, like the first example, but we see that the temperature rises steadily until it reaches a point where there is an abrupt transition to boiling. In particular, distinct coordination patterns can spontaneously develop as a function of a change in a specific variable. A really great example of this is speed. Different coordination patterns can be observed when the speed of movement is varied. This may sound a little complex, but this simply means that by changing the speed of movement, different coordination patterns can be observed in the system. This behavior has been studied extensively in different contexts, and it has been shown that changing a single variable can have a significant impact on the system's performance. So let me put this a little more into context for you. The phenomenon of synchronization is very impressive, yet still very mysterious even in modern times. It has long puzzled scientists and anyone trying to fully understand its complexities. It has been observed in many different contexts, from the movements of birds in flight to the rhythmic movement of fireflies in the night sky. Synchronization is a fundamental concept in the study of dynamic systems. So, this is the process of bringing two or more components into phase or temporal alignment with one another within the system. In order to achieve a stable system, synchronization requires that the different components interact in an orderly manner. This means that the system can maintain an even balance between the different components and will continue to produce consistent results over time. Recently, researchers have been able to demonstrate synchrony using human fingers. A semi-recent study that was conducted in 2004, I believe, researchers used a finger spelling exercise to demonstrate the phenomena of synchronization. Participants were asked to move their fingers in a similar pattern, think playing piano, exactly like that, through different temporal speeds. As the speed of the movement increased, the fingers began to synchronize. They began to sync up with one another, moving in perfect harmony. This suggests that there's some kind of threshold that, when crossed, will cause our fingers to synchronize spontaneously. In other words, out of sync fingers that are moving will spontaneously synchronize after a certain threshold of speed is passed. However, this doesn't mean that it isn't possible for there to be movement of fingers while they're out of sync. This only means that once we pass a certain unknown threshold in speed, that our fingers are said to synchronize spontaneously. Next is system stability, which is a concept that is largely based on the dynamic systems theory. It asserts that any given system is able to maintain its internal state for a period of time, even when faced with external forces. This state of equilibrium is called the stable state, which I will explain a little more in just a minute. But the importance of this concept lies in its ability to provide reliability and predictability to a system, as it ensures that the system will not encounter sudden and drastic changes. So as you can see here, there's an apple on the bowl on the right side of the screen. We can assume the apple is stable in that bowl as long as we elicit no disturbances on the apple or the bowl, such as tapping it. Stability is a concept that is determined differently depending on the context and can be defined in many different ways depending on the field of science it is applied. In the realm of dynamics, stability is considered to be the steady state of a system's behavior. This can be further classified into different types, such as static and dynamic stability. Static stability is when a system returns to its original state after being disturbed, while dynamic stability is when a system continues to move toward a new equilibrium. Knowing this, systems that are stable rely on static stability, while these have the ability to remain in equilibrium even when faced with disturbances. While any system can be disturbed, those that are stable will return back to the initial equilibrium upon removal of the disturbance. A simple example of this is, once again, the apple in the bowl that you can see here on the screen. When left alone, it maintains its position and remains still, probably in the middle of the bowl. But when we add some sort of disturbance, such as tapping the bowl, it moves, but then quickly returns back to its original position. This demonstrates static stability that you can see on the left. On the other hand, we can add some sort of disturbance and the bowl, or to the bowl, and continue with the force to lead to a new equilibrium that you see on the right of the screen, that being dynamic stability. By understanding the characteristics of a stable state, we can learn how the system behaves in a certain environment. This includes aspects such as temperature, pressure, disturbances, and other variables that influence the system. Referring back to the apple in the bowl example, we would take into consideration of the original state of the bowl with no disturbances, just simply an apple sitting in a bowl. This would be the first stable state. But if we tap the apple or the bowl, thus disturbing it, and it tips over the bowl, letting the apple fall out, once the apple comes to a stop and no more movement is occurring, that would illustrate the new and second stable state, the new norm. By observing these characteristics, we can also gain insight into the system's past and future behavior, what we think might happen when we do add those disturbances into the environment, as from what we saw the first time that it happened, as well as what can be done to ensure that the system remains stable and predictable. Ultimately, understanding system stability is essential for ensuring the reliable performance of a system. Attractors are another key element of the dynamic systems theory. Attractors are defined as states of equilibrium or patterns of behavior that a system tends to move toward as it evolves. In a dynamic system theory, the attractor may be a single point, a cycle, or even a fractal pattern. Attractors are important to dynamic systems theory because they describe how energy is dissipated or conserved over time. And you can see a diagram of that here on the screen. Attractors are also referred to as attractor states and represent the stable behavioral state or steady state of the system. For a simple example, we can refer back to our boiling water. The attractors within this scenario are the not boiling water and then the fully boiling water, excluding the transition point in between where we are reaching sufficient temperature to cause the water to boil. This is an example of a dynamic system, which means it has a certain stability and predictability. This is a key characteristic in system behavior as it allows us to model and predict outcomes more accurately. This is a preferred behavioral state in which the system is attracted to one side or the other. This is also where the system is optimally energy efficient, which makes it an attractive state to maintain. An example of this could be a pendulum that you see here on the screen, which once set into motion will continue to swing at the same speed and rate indefinitely as long as there are no external forces or disturbances acting upon it. In dynamic systems theory, this state of steady equilibrium is known as, like mentioned before, an attractor. Order parameters are values that represent the state of the system. They are used to identify the system's state and its stability. Order parameters are used to measure stability because they can define the range of stability for a given system. For example, in a physical system, the force of gravity, such as the hand moving the ball with force enough to reach C and B in the illustration you see here on the screen, may be an order parameter that determines the system of a pendulum's stability and stable state. The pendulum's stable state starts at O, that you can see on the diagram, where the order parameter is the C and B in the image. Any value of the system that could affect and define the stability or movement pattern of the system or pendulum in this case. Control parameters are the features of a dynamic system that determine the behavior of its dynamic state. Control parameters are used to describe the state of a system at different times, allowing it to be analyzed and understood better. In dynamic systems theory, control parameters are essential in describing the behavior of a system as a function of time. They also help to distinguish between different types of dynamical behavior. For example, chaotic and non-chaotic systems. Referring back to the boiling water once again, the control parameter is the temperature of the water. By increasing or decreasing the temperature, it is possible to induce changes in the order of the water. When we're looking at coordination and motor control, it's important to identify the control parameters because it's the basis for being able to assess the stability of the pattern of coordination and for shifting a pattern from one stable state to another. So when we need to understand what is the variable and that is affecting the coordination pattern of the water and what causes the water to make that abrupt change in temperature. Before wrapping up, since we got what I think are the most important pieces of the dynamic systems theory out of the way, I want to talk about a couple more little nitty-gritty pieces of the theory just very quickly since we are on a time limit here. So, self-organization is a small yet fundamental principle of dynamic systems theory. It is the process by which components of a system interact with each other to form an orderly, coherent whole. The components in self-organized systems are nonlinear and adaptive, meaning that they can respond quickly and appropriately to changes in their environment. Self-organization can also be seen as an emergent process in which the system progresses to a more complex and organized state over time. Additionally, coordinative structures in dynamic systems theory are the organizational patterns of movement that emerge from the interactions of environmental constraints, task demands, and limb dynamics. As such, they are the result of a complex, synergistic interaction of many different factors. The coordination of movements is often further refined when the task demands vary or when the context or environment changes. Through this process, coordinative structures allow us to adapt our behavior to the demands of the environment quickly and effectively. Despite its advantages, dynamic systems theory has been subject to several critiques. It is now widely accepted that the interaction between brain and behavior or neurobehavioral processes is complex and dynamic as we take into consideration the many different pieces we've talked about throughout this presentation. This shift in perspective is reflected in the increasing popularity of the dynamic systems theory of human behavior. Proponents of this theory emphasize the mutual bidirectional dependencies between the brain and behavior, the brain being the different pieces and the behavior adding up with the systems. rather than considering behavior to be driven primarily by a single component, such as the brain. This shift in perspective has led to criticisms in reliability. Many new research questions and new methodological approaches to investigating neurobehavioral processes. These include critiques of the theory's lack of focus on individual subjectivity, its difficulty in experimenting with complex systems, and its omission of the social context in which human behavior is situated. In addition, it has been criticized for its generality, with some asserting that it is unable to explain the complexities of human behavior. However, dynamic systems theory provides a framework to explain the interactions between factors that comprise a system and how it is affected by external stimuli. The value of dynamic systems theory lies in its potential to help us better understand complex dynamic research problems. By recognizing that a single cause cannot explain a whole system of phenomenons, we can recognize that many elements interact in complex ways to produce outcomes. This approach to research can enable us to identify, understand, and consider all of the factors that may have an influence on our subject. Through this, we can gain a more holistic perspective on a study and develop more valid concerns about the phenomenon being studied. In conclusion, the dynamic systems theory is an invaluable tool for understanding complex systems and their interactions. It provides us with a way to better understand how different components of a system interact and how changes in one component can lead to changes in the entire system, that cascade that we mentioned earlier, especially within the human body. By using this theory, we can gain insight into how different parts of a system are connected and how they influence one another. This understanding can be used to create more efficient and effective systems, as well as identify potential problems before they occur and develop strategies to prevent them from occurring. So thank you all for listening, and feel free to ask any questions. And listed here are my references used for this presentation. Thank you.